Welcome, everyone. Thank you for joining our August Sea Ice meeting. I am Angela Bliss, a co-leader of the Sea Ice Community of Practice, along with Elaine Runga, Ignatius Rigger, Nathan Kurtz, and Melinda Webster. So the goal of this meeting is to share information about recent advances in sea ice observations in the Pacific Arctic, including talks describing new gridded operational sea ice concentration products for the Alaskan Arctic and new sea ice observations from ship-based platforms. We have two great speakers today, and following their talks, we'll have some time for questions and discussion, and also time to hear updates from community members. So if you have any announcements to share at this meeting, we'll have time to do that at the end. Our first speaker today is Astrid Pacini, who is an NSF Office of Polar Programs postdoctoral fellow in the Applied Physics Lab at the University of Washington. So she'll be giving a talk on the National Weather Service Alaska Sea Ice Program and talking about gridded ice concentration maps for the Alaskan Arctic. So Astrid, when you're ready, you can go ahead and share your screen.
Great, thank you so much. All right, does that look good?
Oh, it looks great.
Great, thank you so much. So thank you all. Let me minimize the Zoom videos. Great. So today, yes, I'll talk about a sea ice data set from the National Weather Service Alaska Sea Ice Program. But before I start, I'd like to acknowledge my co-authors, Mike Steele at the University of Washington, and Mary Beth Schreck, who leads the National Weather Service Alaska Sea Ice Program. So in today's talk, I'm going to focus on the gridding and validation of this data set for the Pacific Arctic. And I'd like to note that I'm a physical oceanographer. So I initially started this analysis because I wanted to find out which product would be best suited for ocean conditions in the marginalized zone. So I'm open to suggestions from the sea ice community. And if you'd like more details, this work is under open review at EGU, the cryosphere. Ooh, there we go. So with that, I'd like to take a moment to distinguish between two main types or approaches to sea ice maps that are commonly used in the scientific literature. So first, we have passive microwave measurements from brightness temperature on board satellites. And these have some pros and some cons. They've provided a great continuous, essentially near daily record since 1978. And so they're a really good tool for analyzing long-term trends or long-term evolution of the ice, since a consistent processing algorithm, whatever that may be, can be applied to a consistent record. But they often struggle during the melt season and in low concentration conditions, so in the marginalized zone. The other type of ice concentration product are sort of blended ice maps, sometimes referred to as operational charts. So these maps of concentration are produced synthesizing all available measurements, including active and passive sensors and in situ observations. And these have pros such that they have high resolution in space and time. We can have a really detailed ice edge, and it provides a good daily state estimate of the ice pack. But the cons include a not consistent record over the historical period because of changes and improvements to our satellite technology, the availability of imagery depending on weather conditions, and even changes in the individual analysts who are drawing the ice edge. So essentially, while passive microwave can give us great insight onto long-term trends, operational products might be better suited to high-resolution daily state estimate of the sea ice pack. So I'll start with a case study. So consider conditions in the Beaufort Sea on August 21st, 2022. So here I'm showing sea ice conditions according to passive microwave, AMSR2 at 25-kilometer resolution, and we see some open water and some heavier ice conditions. Here I'm showing AMSR2 at a much higher resolution, which shows pretty similar behavior where we have this open water area here and some higher concentration north. But ultimately, these two products show consistent sea ice conditions, which is not surprising because they come from the same underlying passive microwave measurements. Next, I'm showing MAISY. This is a blended product from the US National Ice Center. MAISY is binary, meaning that we have a yes, no ice flag and no concentration information. Additionally, MAISY uses a 40% ice concentration cutoff, meaning that pixels marked as open water or blue here have concentrations lower than 40%, and the red have concentrations higher than that. But we already see some substantial differences with the passive microwave maps as compared to MAISY. Now compare these three maps with the subject of today's talk, which is the National Weather Service Alaska Sea Ice Program product, which for the rest of the talk I'll refer to just as ASIP. Sea ice concentration here is broken down into tenths. And when we compare these products, we see that we have very different ice edge among these four, and especially between ASIP and the other three products. Now, I chose this day for a reason, and that's because it was during the NASA Salinity and Stratification at the Sea Ice Edge, or SASSIE field campaign. So SASSIE was working in the Beaufort Sea in August and September of that year. And so in August, SASSIE team members were deploying 4 wave gliders, and I've put a picture of a wave glider here, so you know what they look like. These are autonomous sampling platforms, and they really cannot come in contact with ice or heavy ice. So I've included on here the positions of 2 weeks worth of wave glider measurements, 1 week before this August 21st date and 1 week after. So as you can see, it's really important that we know what the ice conditions are to A, not deploy these assets in heavy ice, and B, to navigate to remotely operate them while the mission is underway. And so depending on which ice product the scientists looked at, it was a very different answer as to where these assets could go. Now, we had imagery available, and what you could see is that there was plenty of low concentration ice in the region that these wave gliders were operating, suggesting that ASIP was sort of the most reliable ice concentration map for this day and this time and for this question. So basically, ice products disagree, especially in low concentration environments. And here, ASIP provides our most accurate ice map. But what is ASIP? So this is an operational product generated by the National Weather Service. ASIP currently they generate daily maps of ice conditions across the Pacific Arctic, along with a range of forecasts, both for the full Pacific Arctic and regional. So here you can see examples of their Cook Inlet sector maps. So from 2007 to 2015, ASIP produced maps 3 times a week, Monday, Wednesday, Friday. And then from 2015 onwards, it's daily. Historically, ASIP has been used for operational purposes, but not scientific analysis. So a lot of ships navigating the Arctic do tend to rely on this data, but we have not seen it used for studies of ice conditions in the Arctic. Prior to this study, to my knowledge, it hadn't been gridded or independently validated, and so that's what I'll show here today. So first, I'll give a brief description of how we processed and gridded this data set. Then I'll present a validation against in-situ observations and compare this product with 2 other ice map products that are commonly used in the scientific literature. So ASIP data are provided as shapefiles following World Meteorological Organization standard with polygons that are described by egg code. And what I mean by polygons is these regions here in this example that are outlined by the black lines. So each polygon has its own egg, which describes sea ice conditions, both concentration, form, and other parameters that one might be interested in. So we take these polygons and project them into latitude and longitude coordinates, as shown here. Then we define a standard grid and grid these projected polygons. So for the purposes of today's talk, I'm going to use a 0.05 degree grid in both latitude and longitude. From these concentration ranges within each polygon, as you can see here, red corresponds to 9 to 10 tenths ice concentration, we take an average value and report that as our gridded ice concentration map here in the example. So I'm happy to talk about how this conversion is made in more detail, but for the purposes of today's talk, we now have this parsed gridded ice concentration product from these shape files. So now that we have our gridded product, let's move on to the validation exercise. So for this, I mined all available in-situ measurements of sea ice in the Pacific Arctic from 2007 to 2022, shown spatially here. These data come from a wide variety of sources, some of which are here on the right. Far and away, the largest contributor to this data set was the IceWatch program. For those who are not familiar with IceWatch, this is a network that facilitates essentially standard ice parameter data collection by observers on board research vessels. So there were 19 IceWatch cruises that transited the Pacific Arctic during this period. And other data sources I've included come from visual observations on board the U.S. Coast Guard cutter Healy and the Canadian Coast Guard cutter Louis Saint Laurent as part of the sub-ice or DBO programs. I've also mined all available data on the Arctic Data Center. And finally, we're also relying on camera imagery from 2 sail drone missions, one in 2019 and one in 2022. It's important to note that ship-based estimates have ice concentration value associated with them, whereas camera imagery on board the sail drone only provides a binary ice, no ice flag. Seasonally, our data are predominantly from summer and fall months, which is unsurprising given the field season. We have pretty good interannual coverage, barring 2012 and 2021. And interestingly, most of our data points come from either open water conditions or heavy ice conditions. So we have this bimodal distribution, and this is a point I'll return to later in today's talk. So how do we do this validation exercise? Here I'm showing an example where we have the Louis Saint Laurent in the Beaufort Sea in October 2015. We find the nearest pixel in the gridded ASIP database, shown by this blue circle, and we consider where the ice edge was according to that product on that day. Then we ask, do the product and the in situ observation agree? So in this example, the in situ observation and ASIP both report that ice is present at that location. So they're in agreement, or ASIP is correct. So to synthesize these calculations, I'll present them using what I'm calling a parity plot. For those who are more familiar with the machine learning literature, these can also be called confusion matrices. But basically, these 4 quadrants will tell us statistically how well a product and in situ observations compare. If observations fall along this green diagonal, then the matchups are correct. So the in situ observation will say no ice, and the map will say no ice, and similarly for ice conditions. Whereas if observations fall along this red diagonal, then there's a mismatch, and the product is incorrect. So what does this look like? We take all the in situ assets from 2007 to 2022, both the binary sail drone information and the concentration-based ice estimates, and we find the following distribution, which generally speaking, we see that ASIP performs quite well against in situ observations with an accuracy rate of about 95%, so very high. But what does this mean? Can we put this in context and repeat this analysis for other data products to understand how ASIP compares to other commonly used sea ice concentration products in the Pacific Arctic? So to do that, we will consider 2 of the products that I introduced in our case study at the beginning. Here on the left, we have the high-resolution passive microwave at 3.125 kilometers. And we have MAISY, our blended product that uses a binary ice-no ice flag around 40% ice concentration. So we'll repeat the methodology for the subsequent data sets. So here we can pull in the AMSR2 ice information, and we already see that these ice edges differ, but this grid cell in AMSR2 also agrees that there is ice at this location at this time. And we can add in MAISY information, but recall that MAISY is 40% ice concentration cutoff. So to compare apples to apples, we also consider the 40% ice contour in ASIP and AMSR2 for this analysis. So we repeat the parity calculation and we limit the data set to the period where all products overlap from 2012 to 2022. And we use only percent-based sea ice concentration estimates. So we throw out the sail drone data because of the need for a 40% threshold because of MAISY. So the resulting parity plots show again that ASIP has a high accuracy rate. When it's wrong, it tends to overpredict ice. AMSR2 has a similar, although slightly lower accuracy rate. And when it's wrong, it tends to underpredict ice. And finally, MAISY looks quite similar to the ASIP product. But to me, having looked at the ice edges on individual days and seen such large discrepancies in the latitudinal position of this ice edge, I was surprised and wondered sort of why are these accuracy rates so self-consistent or so similar, given that we know how much discrepancy there can be. So I think it's helpful to look at 2 examples to address this. So here's an example similar to the one I showed before, where we have an asset very far north, way into the ice pack, far away from the ice edge, where all products where all products agree that this asset is in the ice. Here on the right, I'm showing an example from the U.S. Coast Guard cutter Healy, where all products agree that the asset way far south compared to the ice edge is in open water. So in both of these examples, the asset is very far from the ice edge, despite the fact that these ice edges themselves disagree strongly between products. And so for that, I'll return to this distribution of in situ assets that I showed earlier, where we have a lot of observations at low concentration, or basically in open water, and we have a lot of observations in heavy ice, but we don't have a lot in between. So basically, this asset distribution is skewing our accuracy statistics to reflect the certainty of conditions very far from the ice edge. Now, AMSR2 and ASIP do provide actual sea ice concentration observations and are not just binary products. So I'm going to briefly discard the binary ice-no ice framework and bin the data into 10% ice concentration resolution and repeat the analysis. So here I'm comparing the sea ice concentration from in situ assets on the x-axis with ASIP sea ice concentration on the y-axis, considering that there are, of course, inherent sources of error in both of these values. So if we had perfect agreement between these data sets, the heat map would follow along this dashed gray line. And instead, what we find is that ASIP tends to slightly overpredict ice at almost all concentration ranges when compared to in situ observations. Now we can repeat the same calculation for AMSR2 and we see a different story. We see that AMSR2 instead underpredicts ice for every concentration range, pretty much. And a very simple back of the envelope calculation shows us that ASIP overpredicts ice at half the rate that AMSR2 underpredicts ice. So yeah, ASIP tends to overpredict, but less often than AMSR2 underpredicts. So as described in the introduction, we wanted to assess the performance of these different ice products, specifically in low concentration conditions. So in our case study, we saw that ASIP was better able to capture those low ice conditions compared to AMSR2 and MAISY during the SASSIE campaign. So despite the low number of assets we have in the marginal ice zone, I still want to repeat this calculation for that region. So we again limit the data set to 2012 to 2022 and look at only non-binary or percent-based in situ observations. And MAISY is again excluded because it does not have a marginal ice zone. When we do this calculation, we see that despite not being perfect, ASIP does outperform AMSR2 in these low concentration conditions, even given these sort of low number of in situ assets that we actually have, as seen in this histogram that I showed before. But these results, coupled with the case studies like the SASSIE wave glider example, indicate that ASIP likely does better perform in low concentration environments than its passive microwave counterpart. Now, this motivates the question, on average, in situ observations aside, how far are the ice edges in different products from each other? So to answer this question, I'm going to define a new frame of reference as longitude following. So what I mean by this is that for each band of longitude, shown here on the x-axis, and for each day of the year on the y-axis, I compute the latitude of the ice edge. So in this case, it's the latitude of the 40% ice edge. And so in color, what we see is that over the course of the winter and into the spring, the ice edge begins to retreat and move northward until it reaches sort of the close to 80 degrees north, and then begins to advance over the course of the fall and into the winter. Now, we can repeat this calculation for a different product. So this is AMSR2, 40% ice edge, and we can take the difference of these two, essentially taking the north-south distance between the ice edges of two products here. Now, we take a longitudinal average to obtain one value per day, and we can get a time series of the mean distance between ice edges for two given products at a given threshold. So that's what I'm showing here, where we have distance on the y-axis and sort of month of the year on the x-axis, and blue lines or blue time series indicate one specific year's worth of data, and the red is the interannual average. Negative values tell us that ASIP is further south than AMSR2 in this case. And what we see is that the interannual average reveals that sort of the ASIP ice edge is generally further south than the AMSR2 ice edge, but this is much more pronounced in summer months where we can have up to 185-kilometer distance between the ice edges on average, which we see here, which is unsurprising to us given what we know about passive microwave struggling in low concentration and melt conditions. That said, this puts a number on it. We can repeat the calculation for another matchup. So this is the ASIP and MACI, and we see a similar, albeit dampened pattern, where ASIP is generally further south, and that's generally more pronounced in the summer compared to the winter. So in conclusion, we presented a parsed, gridded, and validated National Weather Service Alaska Sea Ice Program ice concentration dataset, and compared it against a wide variety of in situ assets across the Pacific Arctic. We saw that all three products considered, so ASIP, passive microwave, and another blended product, perform similarly against in situ observations, but that this performance coherence is probably partly due to our asset distribution being either in open water or in heavy ice. And we saw that ASIP outperforms other products in low concentration environments. In situ observations aside, we also saw that ASIP systematically has an ice edge that's further south than both the AMSR2 and MACI ice edges. So I'd like to conclude with a comment or a request to the community, which is that please consider taking ice watch observations while on your field programs. These data are very, very valuable. And I think this segues nicely into Liz Westbrook's talk next, where she'll describe a new mechanism to detect ice from radar measurements. So thank you for your time, and I'm happy to take questions.
Thank you so much, Astrid. That talk was great. We have time for one or two quick questions before moving on to our second speaker. So feel free to put those in the chat or raise your hand if you have a question for Astrid. I have one to start with. So the footprint size of the passive microwave sensor is quite huge compared to one in situ asset or one in situ observation. So have you thought about a way to make it feasible to maybe take many sensors out there or assets to collect ice concentration over something similar to a footprint size to kind of get the average of that to make an easier comparison to the satellite?
Yeah, thank you for your question. That's a great question. And I guess I have two sort of thoughts on that. The first is, yes, absolutely. And so the sort of first way we tried to tackle that is that actually in all of these analyses, I didn't have time to talk about the details, but we've taken a daily average of in situ observations. So I'm never comparing one in situ observation against the satellite grid cell, because that didn't seem like a fair comparison. Also because we could bias with assets that took more frequent measurements as compared to assets that took less frequent measurements. So that's sort of how we tried to address that problem a little bit in this study. But yes, I think it would be really exciting if we had a way to take multiple measurements across a grid cell, because you might imagine also that a ship would preferentially either be moored up to an ice flow and be taking high, the ice watch observer would, record high ice concentration conditions, but perhaps somewhere else in that grid cell footprint, there's a lead, or, if the ship were trying to transit, would transit in more open water conditions. And so you would get very different ice watch results. So it would be very cool if we had simultaneous measurements, say at 4 or 5 points across a grid cell. But I did check all in ice watch data, and I didn't find any that overlapped in a pixel.
Yeah, great, thanks. So I'll address one more question that was added to the chat. From David Douglas. So as for the ice presence absence, are ASIP and NSIDC MIZ products roughly the same in the region of overlap?
Yes, thank you for your question. So I didn't look at the MIZ product specifically. I looked at MACI, so I don't want to speak to the specific MIZ product, but with the MACI example, yes. Let me go back. MACI and ASIP do perform relatively coherently or similarly, given the in situ observations that we have. ASIP has 129 correct matchups, and MACI has 127, but then in the no ice conditions 43 and 44. So they do perform quite similarly, but I have not done this analysis for the MIZ product specifically.
Great, thanks. And we have another question from David, but we'll come back to that in our discussion part. Thank you so much, Astrid. That talk was excellent. And now I'll pass it to Elaine to introduce our next speaker.
Thanks, Angela. Hi, everyone, and thank you so much for joining. I would like to introduce Elizabeth Westbrook. She's a research technician at the Physical Oceanography Department at the University of North Carolina Wilmington. And the talk is going to be about S-band radar detection of sea ice during the SASSIE field campaign. So I'm very excited to hear more about it because I have no idea what this is going to be about. The floor is yours, Elizabeth.
Thank you so much, Elaine. I'm just going to share my screen here. Oh, there we go. Okay, hi everybody. My name is Elizabeth, or Liz. I work at UNCW as a research technician, and just like Elaine said, today I'm going to be talking to you about the radar detection of sea ice during the SASSIE field campaign. So I'd just like to take a minute to acknowledge all the other people who have worked with me on this project. Emmett Colhane at Woods Hole Oceanographic Institute has really been working a lot on this with me, as well as Carlin Schmigdahl, Frederick Bam, Peter Galvin, Kyla Drushka. Yep, so let's get started. So the beginning spark of this project was the SASSIE field campaign. I did a lot of work to help get some of the data from this campaign published. And this was a really big campaign with 7 shipboard sensors and 6 remote or drifting platforms, as well as an aircraft campaign. And the whole goal was to better understand the ebb and flow of sea ice based on temperature and salinity data in the Arctic. But today I'm just going to be focusing in on one specific instrument that we had on the ship, and that is this S-band radar that you see here, and how we use that to sort of make an in situ ice product from this campaign. So the S-band radar is there primarily to help the captains of the ship navigate safely through the ice. So just like the ASIP product that Asher just discussed, it's mostly for operational purposes, but here we've kind of reverse engineered it for scientific purposes. And the SASSIE scientific team started to do this by taking screenshots of the S-band radar every minute or so throughout the campaign. So here you see just a raw screenshot of the S-band radar. The ice is represented by these red blobs on the screen, and you can see that all the metadata is mostly here around the sides. So there's not latitude, longitude, and time data is not really digitally incorporated into this at all. So Kyla Drushka over at UW-APL did a lot of work to help get these screenshots into a usable L4 product, which we have published on PODAC. And that is over here. You can see this is the same from the same timestamp. Here's the finished L4 geotiff. This is what they look like. All of the metadata, time, latitude, longitude is all digitally incorporated into this L4 product when you download it off of PODAC. So this was a tremendous amount of work. And when she was finished doing this, we ended up with nearly 25,000 of these L4 geotiffs, which have the sea ice represented by white pixels and no sea ice is represented by black pixels. Each of these geotiffs, typically they cover about a 3-kilometer radius, but as I will discuss with you in a little bit, some of them have a shorter or a wider radius depending on what the captain's preference was or what the sea ice conditions were. And that was one of the challenges that we faced in analyzing these. So these are just 2 examples. A very distinct advantage of having the S-band radar data in this format is that you can look at any time during the campaign and see exactly what the ice conditions were and what kind of flows were around the ship and things like that. But there's also a real disadvantage, and that is that there's 25,000 of these images, and you can't just look at them in a time series and kind of understand the development of the ice throughout the campaign. So that was where this project got started. We really wanted to take these images, these L4 geotiffs, and turn them into some sort of summary time series product that we could use to compare to, say, temperature and salinity data from the cruise. So our first thought was to do a simple pixel analysis of these geotiffs and, say, take the concentration of white pixels versus black pixels in each image and try to get the ice concentration off of the image from that. But we very quickly found out that that was sort of a naive thing that we thought we could do, to just take pixel concentration and turn it into a time series. And that was mostly because of three main challenges that we faced in doing that. So I'm going to go through those really quick and just explain why that wasn't possible for us. The first thing is this leading edge issue that we see in these images. So these are two S-band radar geotiffs. They're taken 7 minutes apart or so. And in each one, I've marked where the ship is in the other image. So this gray dot and this red dot are in the same geographical location. And similarly, this gray dot and this red dot are in the same geographical location. And they're only 7 minutes apart, so the ice conditions really haven't changed. And just as a reference, I've circled here an ice flow, this kind of heart-shaped ice flow that is the same in both of these images. So you can see where the ship is in relation to that. So you can see that in image 1 here, taken in the beginning, the ship is not really inside of this ice patch, and it is mostly in open water. And this area down here looks pretty sparse. There's much more ice concentration there compared to up here, but it's definitely not this dense, right? And similarly in this image, it even looks a little bit more dense here than it does here, even though these are the same place, same ice conditions. So this is because the reason why we see this is because of the leading edge issue. And that is basically that, like the human eye, the S-band radar sees ice that is closer to it as being larger. But unlike the human eye, there's no brain behind it to correct for that. So a lot of these images show a much higher concentration of ice near the ship than is actually there. Or it may not see some ice flows that are in fact there, like you see these that came into the picture later and are not here, just because it might be hidden behind something else. So that's the leading edge issue. The next thing I wanted to discuss is sea clutter, which is basically just noise on the S-band radar. You can see it in both of these images here. It's mostly common when the ship is in open water and maybe there's a little bit more wave action. So here, these that you see around the side, those are probably real ice flows, but most of the stuff here in the center is going to just be noise. So obviously if you're doing a pixel analysis and you're just taking white pixels versus black pixels off of this image, you're going to see that there's ice concentration near the center of the image when actually there's not. And finally, as I said before, this is mostly an operational instrument, and it's being used by the captains of the ship to make sure that the ship is navigated safely through the ice, which is, of course, the first priority. So the settings of the radar are subject to change depending on which captain is piloting the ship at the moment and what the ice conditions are like. So these images here are taken just 1 minute apart from each other. But obviously the captain has zoomed in on the area around the ship. So the radius shown in this image here is in this blue circle here. And this is going to show up as having a much higher ice concentration than this image, even though they're actually exactly the same. So all of these things, these three things that I've just discussed, are the reasons why we decided that a simple ice pixel analysis would not do to make this product. And we moved on to trying to use machine learning methods to do this. And in order to make this machine learning friendly, we had to move away from a sort of quantification of ice concentration and move more towards a qualification of what the ice conditions were like on these 4 basic levels that I have examples of here on the screen. So we decided that we would classify each image as a C0 for concentration 0, C1, C2, or C3. And that we were going to try to train a machine learning model to recognize these 3 different classifications. So just to go over these really quickly, a C0 is basically no ice, no real ice, just open water and sea clutter, or sometimes you can even see some of the wave gliders or other instruments on the screen as well. So we tried to include those in our training data set, that the C0s would mean no real ice is on the radar. C1 is just when there's very low concentration of ice, a couple of ice flows around the ship, probably not even immediately next to the ship, just there's an ice flow on the screen, but there's very sparse ice, then it's a C1. A C2 is when there is a medium amount of ice, but it's either not very close to the ship or it's not very dense. So here are 2 examples of C2 images. You can see in this second one here that there is sort of dense ice on the radar, but it's not close to the ship. And finally, we reserved C3 for a classification that means there is dense ice and it's right next to the ship, and we're currently traveling through it. So those are the 4 different classes that we used. And we went ahead and worked with a VGG19 convolutional neural network. So I'm actually not a machine learning person really, but that's a 19-layer convolutional neural network that Emmett Colhane at Woods Hole Oceanographic Institute trained for us and helped us develop to do this. So I assembled a training data set of about 1,100 images, including about 200 to 300 from each of these classifications, and then a much smaller testing data set that we used to evaluate how accurately this model could predict the classification of different S-band images. And we tried to include good examples of these 3 issues that I just discussed with you. So once that training was done, we tested it, and this is just a quick breakdown of how that went. So here's each of the 4 classifications. We have C0, C3, C2, and C1. And you can see the number of examples total in each of these classes, and then the number that the model got correctly. So I, just to summarize this, C2 was the hardest for the model to predict accurately. I think this makes sense because it's probably the classification that has the widest range of actual ice patterns. So there was some trouble there, but overall the model was 91% accurate, and it never predicted a classification that was more than 1 step away from the true classification. So we were pretty happy with this. And we went ahead and ran this model on all of the images that we had, so nearly 25,000 of these, and we ended up with something that looks like this. So this I know looks a little bit messy. I promise it will get better in a minute. But this barcode-like thing is the plot of the time series that comes out when you just do 0, 1, 2, and 3. So here on the side, we have the ice concentration ranking that the model produced. And then down here, we have the date throughout the campaign. And this black line is the connected time series of that classification. And here, this blue line down here that you see is just a time period when the S-band radar was off. So we don't have a record for that on the S-band radar, but we do know that the ship was in open water. So that's why I have it down here at a C0. That's why it got turned off. So because this is so messy and it's really hard to see what's going on, we took an hourly average of this classification. So even though a 2.5 doesn't exist on our classification scale, we took an hourly average so that we could actually see how that ice concentration was going up and down. So you see this is the same thing here. We have ice concentration ranking now with in between decimal places on the y-axis and the date of the cruise on the x-axis. So now we have this product, and we're really excited about this because we can see now a time series of what happened during the cruise as far as where the ice was related to us. And the next step was to validate it in some way. So we wanted to know if the model was actually telling us when we were in ice and we actually were in ice. So there were hundreds of pictures taken during the cruise by different people, and there were also ship log records taken by the people on the ship telling us when the ship was in ice versus not in the ice. And so I went through these and assigned classifications to the ship log comments as well as the photos. So I have examples here of 1, 2, and 3 classification photos. So we called this a 1 because there's a little bit of ice, but it's far away. A 3 because there's ice right up next to the ship and it's very dense. And a 2 because there is a sufficient amount of ice, but it's not right next to the ship. And it's a little bit more sparse. And then same thing here, there's just records here. So concentration greater than 50%, I called that a 2. But alongside an ice flow and drifting with the ice, that, and the ship aborted that because there was too much movement of the ice, that was a 3. And then use that ground truth data to go ahead and compare to this curve that we have. So in this picture, this is the same that you saw before, except there are observations shown in blue and red here. So observations that came from photos, I have in blue dots, and observations that came from the ship's log, I have in red dots. And I just want to note too that the ship's log, because sometimes when somebody recorded something on the ship's log, they would round by the hour. So if it was 11:25, they might say it was actually noon or something, or 11:30. There might be a small time difference between the red dots and the actual ice concentration. So we thought that this looked pretty exciting because the ground truth photos and ship's log comments are agreeing with the curve that came from the S-band radar model data. And after we saw this, we decided to go ahead and compare this to the data that came from the other instruments on the ship. So the first thing that we looked at was temperature, or sea surface temperature. Here you can see sea surface temperature in the orange line is represented by, or it represents the temperature that was recorded by the TSG. And the black line represents the temperature that was recorded by the salinity snake. So there's a little bit more fine detail in the salinity snake measurements. And then here, temperature is here on the secondary y-axis. So we thought this was pretty cool to look at because you can see that temperature and ice concentration ice concentration ranking kind of anti-correlate to each other in this plot here. And that makes sense because we expect that when there's a lot of ice, the temperature will cool down, and when there's not ice and we're in open water like we are in this area here, that the temperature will be higher. And we did the same thing with the salinity data that came from the TSG and the salinity snake as well. So you can see similarly here, when we're in open water, the salinity is much higher than it is when we're around the ice. And this isn't quite as strong of a relationship that we see here, but we thought that this was pretty neat to look at as well. And then finally, to tie everything back to Astrid's talk that she just gave, we think that this could be a really useful thing for validating some of these satellite products. And I wanted to show you all this comparison to the NWS gridded product that Astrid has been working on. So here is that hourly average ice classification again from the S-band radar on this side. This is the ship track of the RV Woldstad during the SASSIE campaign. And you can see at the time that the ship was there, what the S-band radar and the ML model that we worked on said the ice classification was. And I know that's from 1 to 3, and the NWS product is from 0 to 90, and a concentration. But here's just based on the colors, you can see when the S-band radar showed that we were in a high ice concentration, or we're in a much lower ice concentration. And then here on this plot, we have the same ship track, but the values have been extracted from the gridded NWS product by Carl and Schmidl. And you can see that they kind of agree when the ship is in ice and when the ship is not in ice. But you can see some more details here. And yeah, so we think that this might be a really useful way to help validate these satellite products. And thank you very much for listening, and I would be happy to answer any questions you might have.
Thank you so much, Elizabeth, for your fantastic presentations. Are there any? I think we have time for a quick question, either here or in the chat, before we're opening up to general discussion. It doesn't seem like it for now. Then I think we can just open it up. Thank you again so much, Elizabeth. And then we can open it up for the discussion, I think. And maybe we can just start with the question we didn't have time for before, for the first presentation to Astrid, and it was from David Clemens, and he was wondering if you've also taken a look at the airborne or satellite high-resolution optical imagery, or if there's a reason to exclude this.
Yeah, thank you for the question. I have not looked at that data. I mean, I've thought about it. It would be really, really awesome to do this comparison, but it was just sort of outside the scope and the timing for this project. But it would be a very cool validation exercise, but I have not done it, no.
Thanks, Astrid. Is there any other questions to either of the presenters or something else you would like to throw in to discuss? Doesn't seem like it. We can give it a little more time, but I wanted to thank again our two presenters for taking the time and sharing their knowledge and their research with us. It was very fascinating to see, and thank you very much for that. And if there's no points for the, oh, Angela, of course.
Yeah, I have one more question for Astrid. So for your gridded version of the product, is that something you will make available?
Yes, the plan is to make that available once the paper gets goes through the peer review system. And I put my code on GitHub, so hopefully people can do the same analysis, but choose so not arbitrarily, but what I presented today was at a specific grid resolution, but in theory, you could then just tweak the grid resolution and make a gridded product in whatever resolution you'd like. So yes, the data will be available very soon.
Awesome, thank you.
I think there's one more question. I'm so sorry, I'm gonna mispronounce your name. Kayorak Jessica, sorry.
Really close. I'm not gonna turn my camera on. I'm feeding my baby. But the question I have is for it was already answered by Astrid, but for the sea ice one, are you planning on making the methods and product available to other ships that may need to know how far away the sea ice is?
That is a good question. So we have talked with NOAA about that. That said, so National Weather Service already does that for a lot of the ships in the area. So that's sort of more their jurisdiction. Of course, if they wanted to look at this ice concentration version instead of the sort of World Meteorological Organization ice concentration ranges, then these data would be useful. But as of right now, I believe and have seen on ships like the Healy and the Sukuliak that these data are being accessed already through the National Weather Service portal itself. Does that answer your question?
Yes. Brianna.
Ignatius, would you like to take over?
Yeah, just a quick question. So Astrid, when we fly with Coast Guard and next week we're flying with Air National Guard, we take lots of pictures. Some of them are geolocated. Would that be useful?
I think that would be amazing. This is something that, we've talked about in this analysis is, any available imagery of ice concentration data in situ is very, very valuable. I mean, the other thing we've thought about is ship cams like the Healy's Aloft cam, which takes an image every minute or so. So I think there is future work to do in that. I do think it would be really, really useful for future validation. Yes.
Okay, yeah, because we could we could easily geolocate them. Well, I think we could geolocate them if we, because we're running a GPS and could geotag or the images afterwards, like in Lightroom. But we also have lots of planet images.
Yeah. And I think, this could be somewhere, I'm not a machine learning person, but maybe Liz can comment. It could be a cool place to bring that in and have it tag images. Because going through, at least I tried to go to the Healy image Aloft cam and decided very quickly
Yeah.
it's not a pathway forward. But yes, I think that would be really valuable.
Yeah, the plane images are wonderful, just because you see a broader area than like the Aloft cam.
Yeah. And
So-
to Angela's question earlier, right, to maybe get more data in a larger footprint.
In an area. Yeah. Yeah. Planet would be like a pixel for for most of the analyses.
Maybe we could talk.
Yeah, we should talk later.
That sounds great.
Great, thanks so much. Again, to Elizabeth and Astrid, I think we might move on to the team updates that Angela is going to take over.
Yeah, so we'd like to use this time at the end of our meeting to share any updates you might have that you'd like to share with the participants of this meeting and with the community. So to start with, I just put a link in the chat. The CQ Field School applications are now open. This is a sea ice field school that will bring together experts and learners with both in the Indigenous knowledge space as well as the scientific knowledge space together to work and learn about sea ice. So applications are due for that September 15th. The link there goes to Melinda's post where you can find a lot more information about this field school. But please, if you have other announcements, now's the time to share.
Angela, can I pop up my screen really quick?
Sure, go ahead.
Who's moderating this? Let's see, let's go with this. Yeah, so as I mentioned earlier, just a little bit ago, we're flying next week. We're going to fly this line to fill the holes on the Russian side. And then we're also flying in this area with the Air National Guard on the second day. But yeah, Scissors flew last Tuesday over this line. And then the Canadians flew in this area a week ago. These little red squares, diamonds around some of the buoys are buoys deployed by the Air National Guard. So this is a wonderful asset to just, help us fill the holes in the array. And then this last map kind of shows our rough flight plans for next week. Blue line will fly on Tuesday, purple line, we're going to fly on Thursday, and there's some ice islands in the neighborhood, which we'll try to fly over, which are marked by these snowflakes. We'll try to run the altimeter so we can get a rough height of these things. But yeah, there's we're seeing a lot more of these icebergs in the Beaufort, and it's a pretty new effort for the program to try to tag these and track them. So this is work with Maribis Schreck at the Sea Ice Desk and the Canadian and US National Ice Service. That's it. Thanks.
Thanks, Ignatius. Anyone else? All right. Thank you so much, everybody, for joining this meeting. Thank you again to our speakers, Liz and Astrid. Those are really great talks. And we really appreciate you sharing your recent work. All right. Thank you all.
Thank you, everybody.
Bye.
Thank you.
Thank you.
Thank you.
Bye.